So now that you've had a chance to graph your trig functions, the sine and cosine functions, I just wanted to quickly go over the coordinates that you would have plotted. Using radians, trig graphs are usually labeled in radians. So we have 0, this is pi over 2, which is 90 degrees. This is pi, which is equivalent to 180 degrees, 3 pi over 2, and 2 pi. Same on the graph below. So if we take a look at that for 0 radians, the sine is equal to 0. That's the point 0, 0. So one thing you need to know is that the sine curve will always start at 0. Then we plotted the points for pi over 6, which is 30 degrees, pi over 4, which is 45 degrees, and pi over 3 at 60 degrees was 1/2, radical 2 over 2, and radical 3 over 2. And those are those 3 points right there. And then we had at pi over 2, the sine value is 1. Keep in mind that every coordinate on the unit circle is has a sine value, which is the y value. So on your unit circle, this is basically what we're looking at for sine. On the unit circle, this is the point 1, 0. Right here is the point 0, 1. Here is the point -1, 0. And down here is the point 0, -1. And then if you go around the unit circle, you'll come back to 1, 0. So essentially you start here and you travel around the circle and you get back to the beginning. And then what can happen is you might go around the circle again. So a circle is just the rotational path that you're taking, but you'd be going around the circle over and over. So if you think of maybe like the wheel on a train, if you put a sticker on the wheel right here, and the sticker went around, and then when it got back to here, it would go around again and over and over and over. So what would these points look like if they're laid out on a graph? They're not going to form a circle when they're actually on a graph of just the sine values. So the sine value is coming from the point, the y value of each coordinate. So here, the sine is 0. When we get to 90 degrees, the sine is 1. So 0, then 1. When we go to this point here, the sine value is at 0. And then when we get to this point at 270 degrees, the sine is -1. And then we're back at 0. So even though when we go around, we're plotting all of these points in between, the points at the 4 coordinates, or at the 4 on the axes, the x and y axes, those points are really important for us to get to familiarize ourselves with. So by plotting every point here, we get this point has a sine of 0. This point at 90 degrees we're at 1. Then we're at 0, -1. So these are the 4 spots on the XY axis as you're going around. This is the x-axis, y-axis, x-axis, y-axis, and then a 5th point, we get back to the x-axis again. So the x-axis, the y-axis, the x-axis, the y-axis, and then back to the x-axis. So your graph should have essentially been kind of curved like that and come down, and then curves, and then goes back up. So it looks more like a wave than a zigzag. It's important, so I want to just show you again that as you're going around the circle, if we're just looking at the sine values, if we start here with our initial value right here, the sine is 0, and then as you go around the circle, then the sine would be 1, then 0, then -1, and then back to 0. So that's how we graph sine: 0, 1, 0, -1, and back to 0. If we wanted to go around the circle again, we could keep that movement going. From 0, we then go around a second time. So from 360 degrees, if we went 90 degrees more, we'd be at 1 again. And if we're 90 degrees more, that's 540 degrees, we'd be at 0. So I could potentially, this is 1 rotation around the circle. If I went around again, we would get to 1, and then at 540 degrees back to 0. And I know that this path would continue in that kind of wave motion. The other possibility is that the circle, you're rotating instead of in a positive degree, you're rotating in a negative degree down this way. So we learned that you could start here, your initial value, but you could rotate clockwise around the circle, and that would be negative. So what if I go down first? This would be negative 90 degrees. I would have gone from 0 to negative 1. Then negative 90 again will get me to negative 180. So I go 0, negative 1, 0, then back to 1, then back to 0. So I'd be rotating around the circle this way. So what would that look like? I'd start at 0, then to negative 1, then back to 0, then to positive 1, and then back to 0. That would be a rotation in the negative direction around the circle. So that's a sine curve, but what we saw is that from 0 to 360, or 0 to 2 pi, is actually 1 rotation around the circle. So this is kind of what we sketched first, but then we saw that we could keep going positive, or we could rotate in the negative direction that way. But if you can understand that sine is really just a graph of these main points, and then we do plot the little points in between. And that forms a wave. So let's look at cosine. Now we'd be looking at the values from this table. So cosine, those are the x values. So I'm going to sketch another circle here. For cosine, if we were looking at the unit circle and we start here, that's the point 1, 0, and then we go at 90 degrees, we'd be at the point 0, 1, and then 90 more degrees, we'd go negative 1, 0, and then the point 0, negative 1. So if I plot the points that represent cosine, those are my x values. So starting at my initial side, which is always your positive x-axis, the cosine value was 0. I'm sorry, it was 1. Cosine value is 1. And that's this point right here. 0 radians, the cosine is 1. But then we got to our 3 points in quadrant 1, which were 30 degrees, 45 degrees, and 60 degrees. That's equivalent to having pi over 6 radians, pi over 4 radians, pi over 3 radians. And then we get to 90 degrees, and that's pi over 2. So what were those values? Were radical 3 over 2, and then radical 2 over 2, and then 1/2. And then at 90 degrees, our cosine was 0. And those points repeated, the radical 3 over 2, radical 2 over 2, and negative 1/2. Sorry, these were negative. And then we got to 180, which was negative 1. So the key points here would be, again, on the x and y axis, would be these points right here. So 0, 1, and then pi over 2 comma 0, and then pi negative 1, and then at 3 pi over 2, we'd be back at 0, and then at 2 pi, we'd be at 1. So as we go around the circle, starting here again, just one more time around the circle, we're moving positive direction around the circle. Our cosine values would start at 1, then go to 0, then negative 1, then back to 0, and then we get back to positive 1. So that's what this is showing us here. So when we sketch that curve, it looks like that. That's 360 degrees. That's 1 rotation around the circle. All the cosine values, 1 rotation around the circle. And notice for both of these graphs that this point right here is 0 degrees and 360 degrees, you're back at the same point. So we start at 0, we go around, 90, 180, 270, back to 360 is the same spot as 0. Okay, so if we were to continue that pattern, again, at every 90 degrees, kind of look at what cosine is. Cosine value is 1, then 0, then -1, 0, back to 1. What if I went around the circle a second time? So that'd be 450 degrees, then 540 degrees. Cosine would go back to 0 and -1 again. So from here, 0, and at 540 degrees, you'd be at -1. So the pattern would continue. We could rotate around the circle in a negative direction. I'll do that in green. So that means we would start on the circle right here and go this way. What points will we hit? Well, we'd start at 1, which is right here. Then 0, -1, 0, then back to 1. So 0, -1, back to 0. I'm sorry, 0. Oh, I messed up again. 1, 0, -1, then back to 0, and then back to +1. So the curve would then look like this. I'm going to give you a visual for what is actually happening here that might help you a little bit. Graphs of sine and cosine. So this is a sine graph. And instead of having a radius of 1, this isn't the unit circle. So a unit circle has a radius of 1, and it goes from 0 to 1 to 0 to -1, back to 0 in one rotation. When I change the radius, that's going to be called amplitude. So a smaller circle is going to have the graph won't go up as high. So right now, this graph is showing us a radius of 20. This circle has a radius of 20, so it goes from 0, the highest it goes is 20, and then 0, -20, and back to 0. If I change the radius to 100, now you see this is a rotation around the circle, and these are all the points being shown by the height of this arm right here. So if it's a radius of 100, we start at 0, 100, 0, -100, 0, 100, 0, -100. So on the graph here, it goes 0, 100, 0, -100, back to 0. But for sine, we're always starting at the origin. That's because you're always starting with your initial point to the right, which has a coordinate at the unit circle would be 1, 0 for this graph. It would, with a radius of 100, this point would actually be the point 100, 0. So write 100, and then we don't go up or down. So let's look at, I guess we could take a look at this. Actually, this is in your book, so we'll go over that in just a minute. Let's just look at cosine. So cosine, the values are a little bit different. For cosine, let's change our amplitude to 20 again. So for cosine, if we start at 0, we would actually be starting right here. And that would be the coordinate 1, 0, or in this case, with a radius of 20, it'd be the point 20, 0. So we would start with, at 0 degrees, we'd have a cosine value of 20. So I'm going to push play. And you see cosine starts up here where the length of the radius is, and then it goes to 0, then down, then back to 0, then up. And if we change the radius of the circle to a larger number, then the height gets bigger. Anyway, so that's kind of a rotation going around the circle. I'll come back to this website. It's a really good website, and I think I put the web address in your packet. So let's look at these graphs one more time now that you kind of understand it, and we'll analyze a couple of more things. Okay. Okay, so back to just the sine and cosine curve. And again, for sine, if we're talking about the unit circle, what we're really looking at is a circle whose center is at the origin and has a radius of 1. So that would be the equation of the circle. That's the unit circle, x squared plus y squared equals 1. And it has the center at 0, 0, and a radius of 1. So we have the point 1, 0, 0, 1, negative 1, 0, 0, negative 1, and our sine values are our y values. So 0, 1, 0, negative 1, back to 0. If you can plot those 5 points in that order, so 0, 1, 0, negative 1, back to 0, then you're good, because you now know that sine is going to be a curve and not a zigzag. So 0, 1, 0, negative 1, back to 0. Connect those points with a curve. And what do those points represent? Well, first thing I want to point out is that in each quadrant, we learned the signs of the trig values. So when we did this the other day, all students take classes. And in quadrant 1, everything is positive. Quadrant 2, sine is positive, tangent is positive, and cosine is positive. So where is sine positive? Quadrant 1, everything is positive, including sine. And in quadrant 2, only sine is positive. Quadrant 3 and quadrant 4, sine would be negative. So I want you to take a look at the graph that we just made and just kind of observe that, because this is quadrant 1 from 0 to 90 degrees. And you see that all of the points representing sine between 0 and 90 degrees are all positive. Then you come into quadrant 2. In quadrant 2, you go from 90 to 180 degrees, and all of the sine values are positive. So again, quadrants 1 and 2 are shown right here. This is quadrant 1, this is quadrant 2. Then we get to this point on the circle. So we just went around the circle to here, and now we're at 180. Now we'd be coming down here, where we are now below the x-axis. And if you look at our y values, we go from 0 to negative 1, and then we go back up to 0. So 0 to negative 1, and then back up to 0. And if you notice, this is quadrant 3, from 180 to 270 degrees. We are below the x-axis, so the sine values are negative here. And then this would be quadrant 4 from 270 to 360. We are still below the x-axis. So sine is positive in quadrants 1 and 2 and negative in quadrants 3 and 4. Okay, if we wanted to continue the curve, continue going around the circle, again, we could just plot these same points on the x and y axis. So here's a quick way to make the graphs without having to graph every single point. 0, 1, 0, negative 1, 0, 1, 0, and again, just sketch the curve. And then that would continue. If I wanted to reverse it, that just means we're going around the circle in the opposite direction. 0, negative 1, 0, 1, 0. And again, you see, it looks like you could connect it with like a zigzag, but you know, because we graphed all the points to begin with, that this would be more of a curve. And it would keep going. So let's look at the same thing with cosine. Again, cosine, we start with the point 1, 0, 0, 1, negative 1, 0, 0, negative 1. Now cosine, we're looking at the x values. So we start at 1, then 0, negative 1, 0, back to 1. So 1, 0, negative 1, 0, back to 1. And if we look now at the sines, all students take classes. Where is cosine supposed to be positive? Everything is positive in quadrant 1. Cosine would be negative here, cosine would be negative here, and cosine would be positive in quadrant 4. So quadrant 1 and quadrant 4, cosine would be positive. Just look at the graph and make sure we see that. So here's your x-axis. In quadrant 1, all of the cosine values are above 0, so this is quadrant 1, cosine is positive. This is quadrant 2. We see the points are now below the x-axis, so quadrant 2 is negative. Quadrant 3, the points are negative, and then quadrant 4, cosine goes back up over the x-axis. So we do see that cosine is positive in quadrants 1 and 4. If you want to continue the curve, you just start back at the top here. You go to from 1 to 0 to negative 1. And then you could put an arrow at the end. And from here, 1, 0, negative 1, 0, 1, and so on. Okay, so hopefully you understand what's basically happening here. And again, this right here, represents the radius, 0 to 1. If I change this unit circle, and instead of giving you a unit circle, I give you a big circle with a radius of 20, then this wouldn't be the point 1, 0. This would be the point 20, 0. And up here would be the point 0, 20. And right here, negative 20, 0. And right here would be 0, negative 20. Now if we made a graph of, say, sine, again, sine, we would start at 0. And instead of going 0, 1, 0, negative 1, we go 0, 20, 0, negative 20, and then we can keep going again. That is actually the height of the graph is equal to the radius. That's called amplitude in your graph. So we're going to learn about that now. So if you turn to the next page in your book, let me find it. You can turn to page 22. Actually, I'm looking at what I wrote up here that we can take a look at before we go to page 24. We never talked about on page 23. It says, make some observations about the y-intercept, domain, and range as it relates to the unit circle. So let's look at the graphs again. I'll go back to the page before because we can take a look at the domain, range, and the y-intercepts. All right. So for the sine, and just so you know, this is the graph y equals sine of theta, or f of x is equal to the sine of x. We could write this either way. So this is the sine function. And for the sine function, a couple of important things that you need to know is that the y-intercept is at 0. The domain is the set of all real numbers. We can go left and right forever. So negative infinity to positive infinity. But the range is definitely restricted. So you need to think carefully about the range of this function. What is the lowest that it goes and what is the highest that it goes? And does it actually include those points or exclude those points? So do we use parentheses or brackets? So the lowest point is -1 and the highest point is +1. Those points are both included, so the range is -1 to +1. Okay, -1 to +1 in brackets. For cosine, we could say f of x is equal to the cosine of x, or we could say y equals cosine of theta. You can write the function either way. These are basically the parent functions for sine and cosine are based on the unit circles. So for cosine, the y-intercept is at parent function, it is at 1. The domain, again, left and right forever. And the range would be the same. So the highest point is 1, the very lowest point is -1, but we're going to write that -1 to 1, like that. Okay, now we're ready to go to page 24. This is not page 24, but this is a blank unit circle, which there are copies of the blank unit circle up at the front of the room. I strongly suggest that as you're studying for your test, that you are filling in a blank unit circle as quickly as you can, memorizing every single degree, radian, and coordinate, because during the test, the very first thing you're going to do is fill in a blank unit circle. And then you're going to base all of your answers and all the coordinates that you graph. Everything's going to be based on your unit circle being filled in correctly. All right, page 24. Standard form of a trigonometric function. Good news is that you can cross out tangent. We are not going to be working with any of the tangent functions, so we can cross that out. We're just going to study sine and cosine. So standard form of a trig function is f of theta equals a sine b of x. So y equals a times sine times b of x. We have these two a and b values. A is the number in the very front, and b is the number in front of x. Unfortunately, I'm also going to throw an h and a k in here at some point, which would really then look like this. And you can write this down here. Y equals a sine b of x minus h plus k. So we always subtract h from x in parentheses, and then we have our k outside. So for cosine, it would be a times the cosine b of x minus h plus k. And before we get into that, h is going to be a shift to the left or right. It's going to look opposite because it's being subtracted. K is going to be a shift up and down. So we're not ready to shift left and right and up and down just yet. But we're going to learn what is A and what is B. Amplitude is the distance from the midpoint to the highest or lowest point of the function. Amplitude really is just the radius of the circle. So if you have a radius of 20, then you're not going to go from 0 to 1 for sine. If your radius is 20, you're going to go from 0 to 20. Amplitude is the distance from the midpoint to the highest or lowest point of the function. So we didn't talk about the midpoint, which really, I'll cross out point, it's really called the midline of the function. So for a function, if it's sine like that, the midline is the line in the middle. So if you think about it, this is 0, 1, 0, -1, back to 0. The midline is the line that would run right through the middle of the function. So how high is it from the midline to the highest point? 1. How high is it from the midpoint to the lowest point? How tall is that line? 1. Okay. Period of a function. When the values of a function regularly repeat themselves, we say that the function is periodic. Let me just tell you a little bit about periodic functions. Functions that repeat themselves regularly. Periodic functions. This would include things that's a cycle. Summer, fall, winter, spring. If I were to graph the seasons or the temperatures outside, we would start off in the summer, it would get hotter, then fall would get cooler, then the winter would get really cold, and then the spring it would heat back up again. And then we repeat the pattern. The temperatures in the summer, then the fall, then the winter, then the spring. Summer, fall, winter, spring. And you see that that's a periodic function. That would be temperatures throughout the seasons. Phases of the moon is periodic. The high tides and low tides, so the depth of the water. There's so many cyclic functions in the real world that occur naturally. I don't know if I said the phases of the moon, but they're naturally occurring. Population sometimes follows also a cyclic pattern depending on the time of year. If you might have heard more babies are born in the spring, that's the time of new birth. So all different kinds of periodic functions in the real world. So the period of the function is the length of the piece of the graph that repeats itself. So if we looked at the seasons, like I said, this would be summer, fall, winter, spring, and then it would repeat. So this is the part of the function that would show one period, 1 year. Okay, so the period of the function is the length of the piece of the graph that repeats itself. For a year, it would be 12 months. For sine, for the regular sine function that's based on the parent function of the unit circle, the period is the length of the piece that repeats itself. So where is this repeating? Well, it's the length that goes around the circle. So it's one circle. So 1, 0, 1, 0, back to 1. It's 360 degrees to get around the circle one time. That's the length of one circle, which in radians is 2 pi. So really the length of the function is one trip around the circle. For sine, it's 0. This graph is labeled a little different. So you go pi over 4 is 45 degrees. Pi over 2 is 90 degrees. That would be 135 and then 180. Sorry, so this is 90, 180, 270 here, and 2 pi is equivalent to 360. And then the graph would repeat. So if we just graph one period of the function, that means one cycle of the function. So it's the length of one cycle. make sure you know period is the length of one cycle. So from 0, I'm going to skip 45 degrees and go straight to 90. We know that sine goes from 0, then to 1. Then at 180, we're back to 0. Then at 270, we're at -1. And at 360, we're back to 0. So as long as you can plot those 4 points on the XY axis and then you get back to where you started. 1, 0, -1, 0, back to 1. I said that wrong. 0, 1, 0, -1, back to 0. And then you know this point is not going to be directly in the middle. This is actually at radical 2/2 is up here a little bit more. So you don't connect it like a zigzag, you connect it with a curve. That's the length of one cycle. The length of that cycle, one period, is 360 degrees, or more commonly, we give it in radians, is 2 pi. So what about cosine? Cosine, the length of one cycle. So for cosine, we go around the circle once. That's your x values. So 1, 0, -1, 0, back to 1. 1, 0, -1, 0, back to 1. So we start here. 1, and we're going to skip 45 degrees and go straight to 90. So 1, 0, then at 180, the cosine is -1. Then at 270, you're back to 0, and at 360, you're up at 1. So whatever the graph looks like, you're looking for the 4 axes. 90 degrees, 180, 270, 360. So there's one cycle. So what is the length of one cycle before you go around the circle again? The period would be 360 degrees, or 2 pi radians. Okay. The next thing that we'll look at I skipped the question at the bottom of the page again. So what does the B value tell you, and what does the period tell you? And how are they different? So we're going to need to take a look at the B value, which it isn't up here. So what is the B value? So A is the amplitude. A is the amplitude. Which is the height from the midline. The period of a function is the length of the piece of the graph that repeats itself, so the length of one cycle. Well, the B value, which it's not up here, for the parent function, just so you know, the A value is 1, and the B value is 1. So B equals 1 in this graph. A equals 1, and that's the height from the middle, so the maximum height, more or less. What does the B value tell us? The B value, you're going to have to write this in since it's not up here, is frequency. It's basically the speed at which we rotate through the circle. So right now, from the speed of the parent function determines how we compare every other frequency. So think about, like, your parents may teach you how to drive, or maybe you're driving instructor teaches you how to drive. And you do the speed limit because that's what they taught you. So you're driving and you're doing the speed limit. So your driving instructor drives at this speed around the circle because that's the speed limit. So we'll call that the parent function. But then you learn to drive and you start out driving the speed limit, but then you get your license. And maybe you do something you're not supposed to do and you drive faster around the circle. So you're driving faster. So how in the graph are we going to show that you're driving faster? So let's say I don't recommend doing this at home, but let's say you're driving double the speed limit. You're driving twice as fast as you're supposed to be. How would that show up in a graph like this? So since I started drawing this on the cosine circle, let's just go down here. So that means I'm going to have to show that I've gone around this circle in the time it took the instructor to go around the circle one time. Then I got my license and I felt all confident and I drove around twice as fast. So I'm going to show you how I would represent that. So the double the speed means the B value is 2. We're going twice as fast. That means that instead of going from 0 to 2 pi and doing the same speed as the instructor, I'm going to go 2 times around the circle in the same amount of time it took the instructor. So what's going to happen is it's going to look like this. Instead of at 90 degrees, I get back to the origin. Instead of going from 1 to 0, it takes 90 degrees. From 1 to 0 would be 45. And then 1, 0, negative 1, 0, positive 1. So now I've gone around the circle one time and I did it faster than the instructor. So again, if I'm going double the speed, in the time that the instructor starts from here and goes around once, I'm going to go around twice. So how do I show that? Well, I got to meet him back at the starting point. So I go around again. And what this is showing you is the green curve is the instructor, goes around once, but I'm the orange and I went twice as fast. So my frequency is 2. My B value is 2. Now, what would that mean for period? Well, the period, the length for one cycle was 2 pi radians to get around the circle once, but not for me. The length of one cycle on my graph to go around one time, not mine, yours. You're speeding, I'm not. Okay, the length of one cycle here, I've got 2 complete curves here. So one curve on this graph, the orange, I start at 0, but we ended at 1 pi instead of ending at 2 pi. So one curve goes 0 to pi, which is 180 degrees. So the period of the orange is 180 degrees to go around once, which is 1 pi radians. So the period is cut in half. Well, that means that any time that you want to calculate the period, if it's not 1, if B is 1, the period is 2 pi. But if you increase the speed, that's going to change the period. So here, the period would be what it was originally divided by 2 because I was going twice as fast. So our B value is our frequency. It tells you how much faster than the parent function you're going. How many times do you go around, or how many times something goes around in the same amount of time the parent function went around? So what does the B value tell you? The B value is frequency or speed. It tells you how many times or I'm going to write this a little differently. It tells you how many complete cycles you have. how many cycles there are from 0 to 2 pi. The period is the length of one complete cycle. So B tells you frequency, it tells you how many cycles there are from 0 to 2 pi. Period is the length of one cycle. So let's look at the graph for sine and see if you can understand this. So I graphed the sine function, the parent function, y equals sine x, with an a value of 1 and a b value of 1. So b is 1. That means it goes around one time from 0 to 2 pi. It starts here, and it makes one complete sine curve and stops at 2 pi. So what happens if I increase the frequency? I'll do this in green again. What if I graphed y equals, keep a the same, but I change b to 3? That means I have 3 complete cycles. It's going to be hard for me to do on this graph because this graph isn't split into thirds, but I'm going to do it anyway. Let me think. So I'm going to have to split this into thirds. So it's easier with degrees. So 120 degrees, so 360 degrees. If I split that up by 3, so we take our period and we do degrees, is 360 divided by 3. That means I have to end every 120 degrees. So that's going to be, this is 135 degrees. So it's going to be about here. This is 90, 135, so 90, that's 45 degrees. 10, 20, 30. About right here. So let's say that's about 120. And then I'd have to get to 240. So 180. This is 225. So 240s will be maybe about here. And then 360. So this isn't the best graph paper to work with to show you this. And then I'll show you how we really represent period is not in degrees. So this is if we represented it in degrees. And if we represented it in terms of radians, period would equal 2 pi split into 3 because there are going to be 3 complete cycles. And we would just leave it as 2 pi over 3 radians. So 120 degrees is equivalent to 2 pi over 3 radians. So what would that look like? A complete sine curve from 0 to 120 degrees so that I have 3 complete sine curves before I get to 360. So I'm going to have to split this into fourths. It's going to look, I'm going to do the best I can with just freehanding this and not getting too complicated. Like that. And then the next one has to end about here. So I just went down too far. I went past -1. So just so you know what I'm doing, 0, 1, 0, -1, 0. Then I go 1, 0, -1, back to 0. And then again, to get to 2 pi. So 0, about halfway. So 1, 0, -1, back to 0. So that shows 3 complete curves in the same time it took for the parent function to go around. So here's the end of the first cycle. That's the end of the first cycle. So that would be 2 pi over 3. This is the end of the second cycle. So that would actually be 4 pi over 3. And this is the end of the third cycle, which would be 6 pi over 3, which would simplify to 2 pi. So this is showing you a frequency of 3, means that in the time it took the parent to go around the circle once, you went around 3 times as fast, and that's shown by a curve going faster in the same amount of time as it took the parent to get to 2 pi. The speedy little kid went around 3 times as fast. So B, the frequency is 3, but the period is the length of one cycle, which would be 2 pi split into 3, which is equivalent to 120 degrees instead of 360.